This is Module 5, Lecture Notes 10. Today we're going to talk about the word mole. Okay, you're probably thinking, oh, a mole. I've heard that word before. I have lots of moles on my skin. Or maybe we found a mole in our yard underground, burrowing. The word mole is actually a homophone, and it is also used in chemistry. And in chemistry, the word mole is used as a counting number. Okay, it's a counting number used to count atoms and molecules. And we need a word in order to count atoms and molecules because they're so small. So we need a word in order to talk about them because there's so many of them in even the smallest sample of matter. So let me show you a couple other counting words so you can get a feel for how this works. If I told you I had a dozen of something, you would know I'm talking about 12 of them because this word is used interchangeably with this number. A dozen always means 12. If I say a pair, you would know I'm talking about 2 of something. Or a couple. These are words that relate to a number. The word gross is also a counting number. It's used less frequently, but it means 144. Well, the word mole in chemistry is used the same way. It signifies a number. And the person to come up with this was named Avogadro. So it's often called Avogadro's number. And the number that he came up with is 6.02 times 10 to the 23rd. So he says that when you have a mole of something, you have this many atoms or molecules in that mole. Okay, this is a counting number. And look how big it is. 6.02 times 10 to the 23rd. That is a lot of zeros. And our number needs to be really big when we're talking about things in chemistry because atoms and molecules are so small. Okay, so let's write this in the box. We're going to say 1 mole is always equal to 6.02 times 10 to the 23rd. That is something that you will need to memorize. Let's see how big that really is if we were to write it out in standard notation. So that would mean putting 602. Remember, you just move your decimal place 23 times. So that would mean 21 zeros. Go ahead and count those out in your head. Okay, that's a huge number. And I think it is a sextillion. Okay. All right, so let's continue with counting and see if we can use the word mole now that we know what it means. We'll do some easy ones first. I said, how many apples are in 3 pears? Okay, well, pear means 2. So if I have 3 pears, I must have 6 apples. What about this one? Okay, those are easy. Well, let's work in the word mole. How many beans are in 1 mole? Well, we know that 1 mole of anything, it could be a mole of beans, a mole of eggs, a mole of calculators, it doesn't matter what it is. The word mole means we have 6.02 times 10 to the 23rd. Well, what about how many beans are in 3 moles? How would you do that? You would need to take 3 times this number. Okay, I would like you to pull out your calculator. If you need to pause, go ahead and do that. But we are going to look at how we punch something like this into your calculator, and it is super important. Okay, so we know that we want to take 3 times our mole number. Okay, you're thinking, oh, that's pretty easy to punch in. It is once you get the hang of it, but you need to be really careful with how you punch in this exponent. So let me show you what you should type in on your calculator. You're going to do 3, your multiplication button, 6.02, and then you're looking for a little button on your calculator that says EE. It means exponent. And you're going to press E23. Notice I never typed in times 10. This button means times 10. So watch how I would do this on one of these blue calculators, which I think a lot of you have. 3 times 6.02. My E button is right here in the light blue. So I'm going to press second, E, 23. I didn't do any times 10. This means 6.02 times 10 to the 23rd. You get the idea. You should get this number, 1.806 to the 24th, if you punched it in correctly. If you did not get this number, try using the buttons on your calculator differently, or you may need to ask for help in class with how to use your specific calculator. So the answer is 1.8, we'll round it to 1.81 times 10 to the 24th. So please, please practice how to punch things in correctly in scientific notation on your specific calculator. Okay, so how does this relate back to the periodic table and what we're doing with atoms and molecules? Well, now that we know what a mole is, I'm going to tell you how these masses are related to a mole. This is the mass of 1 mole of these elements. So 1 mole of carbon weighs 12 grams. 1 mole of argon weighs 39.9 grams. Okay? And remember that 1 mole has 6.02 times 10 to the 23rd atoms in it. So here is everything set up for carbon. Carbon weighs 12 grams. It has this many atoms in 1 mole. These can all be used interchangeably. Okay, so let's use what we just learned in some problems. Our first question says, how many moles, I'm going to circle that because that's what we want to find, of sulfur are in 67 grams of a sample of sulfur? So we're going to start by putting 67 grams of sulfur over 1. Ooh, does that take you back to the stuff we learned in the first unit? We are setting these up to be factor label problems. Okay, I don't want grams of sulfur anymore. I want to change this to moles of sulfur. Okay, and here we have our conversion factor. 1 mole of anything is equal to the molar mass on the periodic table. So I need to look at sulfur and put 32.1 grams for 1 mole of sulfur. And that's how we will convert. Always make sure to check that your units cancel. Grams of sulfur, and we're left with moles. Go ahead and do this on your calculator. And we get 2.1. Don't leave any naked numbers. It should be 2.1 moles of sulfur because that's what we were asked to find. Okay. Let's go to the next one together. If I ate 5,000 grams of salt, Gross. How many moles did I eat? Okay. So again, we want moles. And we're starting with 5,000 grams of NaCl. Your first step is always to put it over 1. If you don't want grams anymore, it goes in the bottom. We want moles of salt. Okay, so we are looking for a molar mass here. Where do I find NaCl on the periodic table? I won't find it together like this because sodium chloride is a compound. And remember, these are elements. So you will need to look up sodium and chlorine separately and add them together to get the molar mass. I like to do that off to the side. You could just say NaCl equals 22 for sodium plus 35.5 for chlorine. Okay, so sodium chloride equals 57.5 grams. If you want to round it to 58, that's fine. So we'll do 5,000 divided by 58 for the molar mass, and we'll get 86.2. And that's moles of sodium chloride. I'd like you to pause this and try the third one by yourself. Okay, when setting up this third one, they gave you 12.331 moles of ammonia. You're going to put that over 1. Notice that they gave us moles to start with this time, and they want to know what the mass is. Okay, so if we start with moles and we don't want them anymore, they have to go in the bottom. Okay. 1 mole of ammonia is equal to the molar mass. Okay. This number that goes with moles in your conversion factor is always a 1. 1 mole is equal to the molar mass. Over here, I've added up NH3 and I got 17.03. We can use 17 to make it simple. And this time, you're going to multiply 12.331 times 17. Units cancel, and let's see what we get. I got 209.6. Don't leave it naked. This is grams of NH3. And they asked us to find the mass, so that makes sense. These problems will always be done using a factor label setup. Okay, let's flip over to the back, and we're going to talk about why we even care about moles in the first place. Okay, so the real reason that we need to know how to use moles is because when chemicals react together, they do so in whole number ratios. Okay, remember when we balanced equations, this would be a 1. 1 mole of CH4 reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. A chemical reaction is like a recipe. So many things we use on an everyday basis come from chemical reactions. Think about a medicine you might take. A chemist needs to know what reactants react together and in what ratios they do so in order to correctly produce the products. These coefficients out in front represent the number of moles of a substance that need to be reacted together to produce the number of moles of products. Okay, so you might just put something like moles. The coefficients represent the number of moles. So let's see how we would actually use this in an example problem. It says a chemist begins with 5.6 moles of oxygen gas. And we want to know how many moles of carbon dioxide will be produced. Okay, so we might even put something like we're starting with 5.6 moles of this reactant. How many moles of carbon dioxide will be produced? You see that mole can be abbreviated MOL. You'll often see that written in your textbook or in chemical reactions. So the way you're going to set this up is you're going to put what you know over 1. And we know that if we want to get rid of moles of oxygen, they need to go on the bottom. And instead, we want to end up with moles of CO2. Our chemical reaction tells us how many moles of one substance are equal to how many moles of another substance. And you're just going to use these coefficients out in front to do your factor label method. For every 2 moles of oxygen, I produce 1 mole of carbon dioxide. All I did was use the coefficients from my balanced chemical reaction. This step is called a mole ratio. The ratio of one amount of moles to another amount of moles from a chemical reaction. Solving this should be really easy. You're just going to take 5.6, divide by 2 in your calculator, and you get 2.8 moles of carbon dioxide for our answer. Okay, this last question says a chemist has 0.234 moles of C2H6O. How many moles of carbon will they get when the sample is decomposed? Okay, well, we just learned from our previous problem that if we start with moles of one substance and we want to change it to moles of another substance, we need a balanced chemical reaction to do that. And you notice here, I have not written that for you. This problem puts together so many concepts that we have learned up to this point. First, you're going to need to write the reaction correctly. Okay? Using the word decompose, you should know what to do with C2H6O. Decompose it. Secondly, you'll need to balance it by putting whole numbers out in front to get the same number of reactant molecules as product molecules. And then lastly, now we can solve what they are asking with the mole ratio. Okay, I'd like you to pause and see how far you can get through these steps without my help, and then come back and we'll work through it together. Looking at step 1, I took C2H6O, and I know that the word decompose means to break apart into individual elements. Carbon, hydrogen gas, always a diatomic, and oxygen gas. Now I need to go back and balance. I need to put a 2 here to make 2 oxygen, which will make 4 carbons, and 2 times 6 is 12 hydrogens. 6 times 2 is 12 hydrogens. I would say this balances 2, 4, 6, 1. Now we can start with what we know. We have 0.234 moles of C2H6O, and we want to know how many moles of carbon. Well, we can use the mole ratio just like we did in the previous problem. I don't want moles of C2H6O, so they need to go on the bottom. I do want moles of carbon, so that goes on the top. You will use your coefficients that are out in front. For every 2 moles of C2H6O, I produce 4 moles of carbon. You will multiply in your calculator and then divide by 2. And I get 0.47 moles of carbon for the final answer. So that's all you need to know about moles. Probably a different meaning than you were thinking, but really, really nerdy scientists celebrate Mole Day. It's on October 23rd, 10/23, every year, and they often celebrate it at 6:02 in the morning. Just a little fun fact.